Operating systems demand precision. A Linux shell expects exact syntax to execute a task. Large language models, however, generate fluid, probabilistic text. Bridging the gap between strict system execution and natural language necessitates a layer of deterministic logic that standard API wrappers cannot provide. Giving a standard chat wrapper direct read and write privileges across a file system introduces high volatility. A single hallucination, misinterpreting a delete command or mangling a path structure, can irreparably damage the host environment. Makulu Linux resolves this by deploying the Electa AI Center. Instead of a loose script or a web-based Electron app, Electa ships as a fully compiled, self-contained Python binary integrated directly at the OS level. To understand how it maintains stability, we need to examine its 4-stage routing pipeline and the fail-safe mechanisms that filter every prompt before execution. Embedding the logic directly between the bash terminal and the system daemons ensures that natural language is parsed, verified, and translated into native system calls, bypassing the need for fragile external web frameworks entirely. This schematic maps the Linux stack. Notice the active layer positioned precisely between the user-space shell and the system execution daemons. This is the intelligence layer. It functions as a central dispatcher, continuously evaluating input and routing it to over 30 specialized execution agents, handling everything from Docker container management to local audio control. Because the dispatcher actively analyzes the intent of every message, the user never has to manually toggle the interface into a coding, writing, or system control mode. The engine driving this automatic dispatch is a multi-stage semantic routing protocol. By forcing conversational input through this specific protocol, the architecture successfully converts open-ended requests into mathematically precise system operations. Let's track an input string, clean up my temp files, entering the routing pipeline. It immediately hits stage 1, the keyword pre-filter, performing an O1 hash check for obvious signals. Our request triggers no matches here, passing to stage 2, the AI router. A high-speed model classifies the intent. A regex boundary extraction clamps down on the output, isolating a single routing token. Here, it extracts ask command. This token is one of several discrete targets, alongside general chat, specialized coder, and direct system command. The router also maintains a sticky context. It stores the last 5 routing decisions in a DEC data structure. If you have been writing Python for 20 minutes, the router biases ambiguous inputs toward the coder token, reducing friction during deep work. Reducing verbose model output into strict semantic tokens creates a structural firewall. The execution agents receive nothing but absolute instructions. Allowing a generative model to execute a destructive shell command based on vague user input poses a severe security risk to the host OS. When the router determines an intent is ambiguous, it returns an uncertainty token, like ask command. The terminal halts and presents a bifurcated failsafe. It displays the exact bash command to run, alongside an option to simply explain the process. If the user selects execution, the system runs a mandatory pre-flight file snapshot protocol. It backs up the target directory before a batch operation begins. Forcing explicit user verification at the exact moment of semantic uncertainty prevents total data loss and keeps the user in control of the file system. When the router extracts a coder token, the string is directed into a sandboxed development environment. Upon entry, the agent indexes the current workspace, compiling a snapshot of the file tree and codebase symbols to continuously inject into the context window. For complex feature engineering, the user initiates the /plan workflow, which activates a 3-agent pipeline. The first node is the architect. It consumes the codebase index and drafts a highly detailed technical markdown design, mapping data structures and APIs, without writing executable code. The document passes to the developer agent, which implements the design by actively writing code and running unit tests. Finally, the reviewer agent cross-references the code against the original plan to catch edge cases. When code is actually modified, the system utilizes a surgical /replace execution method, swapping out specific lines rather than allowing the model to rewrite the entire file from scratch. Before the file write is committed to disk, a live color-coded diff preview is generated in the terminal, showing exactly what will be removed and added. Segregating the planning, building, and auditing duties into a multi-agent triad prevents unchecked hallucinations from corrupting a project's repository. Local execution is highly controlled, but routing natural language requires heavy compute. Relying on a single cloud provider's API guarantees eventual failure during server outages. Electra operates on a 9-tier backend provider fallback chain, granting access to 81 distinct AI models. Every 10 minutes, an auto-rotation script pings the providers and dynamically routes traffic to the hardware cluster showing the lowest latency response. If an execution agent fails locally, a background self-repair system activates. It analyzes the stack trace and classifies the issue, distinguishing a temporary network timeout from a missing system package or a core logic bug. If the error is a capability gap or logic fault, the system autonomously writes and compiles a Python repair plugin to patch the issue locally, and silently files a structured report to the main GitHub repository. By combining automatic model rotation with local self-healing logic, the architecture achieves near-zero downtime, regardless of external network stability. When external internet connectivity is lost, the system falls back to a locally hosted Ollama model. Historically, these local backups suffer from context amnesia during long sessions. To solve this, Electra deploys Mempalace. It retrieves the 2 most recent conversation turns from a local SQLite database, establishing short-term memory. Simultaneously, it queries a local ChromaDB instance for 4 relevant vector matches from user history, injecting them to form long-term semantic memory. Injecting this hybrid memory block into the local model ensures that offline operation maintains the exact same continuity as the primary cloud connection. Every component, from error handling to memory injection, routes back through the central AI dispatcher, which acts as a modular foundation for expansion. Through Plugin Engine v2.0, community-written Python scripts can declare themselves as an agent. This injects custom tokens directly into the Stage 2 AI router, granting them the exact same execution priority as native system functions. Because the engine supports hot reloading, these new integrations are loaded instantly into the execution layer, without requiring the new binary to be recompiled. This framework already supports specialized daemons running silently in the background, from systemd service management and local Docker container control to a fully autonomous finance bot tracking online revenue streams. Dozens of peripheral daemons, scripts, and APIs are completely decoupled from traditional command line syntax and routed securely through one central semantic core. By weaving semantic routing into the system architecture, Makulu Linux converts natural language into a reliable control protocol for the operating system and its integrated services.